Hi folks, welcome to what I think is the last lesson in the P4 topic, and this one is about fusion. So we did a little bit, we mentioned very briefly fusion in the previous lesson. That lesson was about fission if you want to go back and watch that. But this is focused on fusion for this lesson, okay? So I want you to be able to describe the process of nuclear fusion, and your starter task is to just translate the key words for this lesson into your glossary. Now I appreciate you've not got that glossary in front of you. Normally this will be accompanied by a little piece of paper, but what I'm going to do is you translate those words onto a piece of paper, and then I'll tell you what each one of them means, and you can write that down on your piece of paper or however you want to do it. So just pause the video, take a couple of minutes, see if you can translate those keywords. The way to do this, by the way, you see that little symbol there? That looks an awful lot like that little symbol there, which is an F. So do that, translate the keywords, pause the video, give it a go. Okay, let's go through those then. So this first word up here, this first word is, it wakes up, fusion. Okay, fusion. So we've mentioned very briefly the last lesson that fusion is the joining of atomic nuclei. So you get two atomic nuclei, stick them together, that's fusion. Word number 2 here, you should have got nuclei. So nuclei meaning the very centre of an atom. Okay, that is the, call it the nucleus, but if we're talking about more than one, it's nuclei, so it's plural of nucleus. And obviously we're dealing with more than one for fusion. If we're joining two things together, there's always going to be more than one, so we're calling them nuclei in these lessons. Proton, you should have had for word number 3, that is a subatomic particle. It's found in the nucleus, it has a mass of 1, and it has a positive charge, positive by 1. Number 4, keyword number 4, neutron, again another subatomic particle, again found in the nucleus. It has a mass of 1, but it does not have a charge. It's not negative, it's not positive, it's neutral. And then finally, isotope is the last word. I've got a slide that describes what an isotope is in a second, but you can just think of it, if you just want a brief description now, it's just like a variant of an atom. Okay, so it's like just like a normal atom, but its mass is usually different. It's got a different number of neutrons. So those are the key words for today's lesson. So hopefully you can come back to those later on if you've made a bit of a note on those. If I start talking about the fusion of atomic nuclei where the proton number changes and neutrons are emitted and it's based on isotopes, all those keywords there have just been used, so hopefully that'll be useful to you later on. So things I want you to do today, it says give yourself a rating. Again, in a lesson I'd have given you a sheet here to do this on, but I just want you to think about each one of these outcomes. Do you know about it already? Where do you stand before the lesson starts? So the outcomes are as follows. So outcome number 1, describe the similarities and differences between fission and fusion. So that's outcome number 1. So think to yourself, can I do that now? Probably not, because we've not done this lesson, but you might know a little bit about it. So give yourself like a rating out of 5 if you like. Outcome number 2, explain the difficulties with using fusion as an energy source on Earth. Do you already know that? If you do, give yourself a bit of a rating in your head. And then outcome number 3, explain how energy is produced via fusion by comparison of reactants and products, and then I've put in brackets E equals mc squared. So if you know all about that, then obviously give yourself a little thumbs up or 5 stars or whatever you want. Before we get started. Right, I mentioned the word isotope a minute ago. This is an atom of hydrogen, and I know it's an atom of hydrogen because it's got 1 proton. And if I go to my periodic table, I'm not going to get the app open, but if I go to a periodic table, in fact I probably should get the app open because I might need it later on. So if I go to the periodic table and I find something that's got an atomic number of 1, meaning it's got 1 proton, I'm going to find that that substance is hydrogen. Okay, so atomic number 1 is hydrogen. An isotope is just a variation of an atom. So what I'm saying to you is, I could have an atom that looks exactly like that and it's hydrogen, but if I found another atom that's still got 1 proton in it, but maybe a different number of neutrons, it's a variation of hydrogen. And I've got an example of that, and that example is there. So if you look at this, there's only one difference between those 2 atoms on the board, on the screen there. You can see that there's a neutron. There's an extra neutron involved. Now look at what that's changed in terms of its atomic number and its atomic mass. The atomic mass of hydrogen is 1, because it's only got 1 particle that has significant mass there. The atomic mass of this, deuterium, which is just an isotope of hydrogen, is 2, because it's got 2 particles of mass. The important thing to remember though is, its atomic number is 1, meaning it's got 1 proton. The atomic number of this is also 1, it's still only got 1 proton. So it's still technically hydrogen, it's just a variant of hydrogen, okay? So as I've put up here, they always have the same number of protons. In this case, these isotopes of hydrogen have got 1 proton each, just like hydrogen has, but they can have different numbers of neutrons. Well, guess what? It's not just deuterium that's an isotope of hydrogen. There's another one as well called tritium, and you can see the difference. It's just got, this one's got 2 neutrons, but it's still only got 1 proton. Okay, so this can change certain properties about the atom, but generally they still have very, very similar properties as it is. Okay, important to note in all of these as well, the number of protons is still equal to the number of electrons. So none of these are ions, these are all still atoms, they're just atoms of isotopes. These two are isotopes of hydrogen. Okay, so that's what an isotope is. Hopefully that summed it up. To be honest with you, this shouldn't be new to you. You should have probably done this in chemistry. If you've not, don't worry too much about it, because, well, I've just described it to you there. So you can go over that again yourself if you're not sure, or you can go and have a look at a bit of Bite Size or YouTube or whatever you want to do to get yourself up to speed on isotopes, because we're going to mention them quite a bit in this lesson. Okay, so this is a nice little animation if it starts. I don't know what's going on with that. Oh, is that working? There we go. So this is a nice little animation showing you the fusion of isotopes of hydrogen. So there's two words there, deuterium, two atoms of deuterium there, nuclei of deuterium I should say, and deuterium is just an isotope of hydrogen. So if the word deuterium is confusing you and you're not sure what the hell's going on, just imagine it's hydrogen, okay? So we've got two of these nuclei that join together, and you can see the numbers of protons and neutrons. Now look at what happens afterwards. That's interesting. You should have noticed a couple of things there. Watch this. Mass before, 4. I've got 4 particles of mass. They combine together, 1 neutron gets emitted, and I'm left with helium. The reason I'm left with helium is because if you look, the red ones that I'm pointing like you can see, the red ones are protons, and after they fuse together, it has 2 protons. Let's go to the periodic table. What's got 2 protons on an atomic number of 2? Helium. So if I take 2 isotopes of hydrogen, and I manage to physically fuse them together, I can end up with helium, and it emits a neutron as well. It also gives out a ridiculous amount of energy doing so. Okay, so this is the fusion of atomic nuclei, okay, and it's got their deuterium to deuterium fusion reaction. You could fuse other things as well, but this is what we're going to be focusing on today, okay? So fusion is just the joining of atomic nuclei. What's interesting is, though, the mass of the products are slightly lower than the mass of the reactants. Now, I'm not saying that the number of particles changes. We started off with 2 protons and 2 neutrons, and at the end you can see there's still 2 protons and 2 neutrons. One of them gets ejected, but it doesn't mean that thing doesn't exist. What I'm saying is, if you was to take those and you had like the best set of scales in the universe, the best balance in the universe that could measure amounts of subatomic particles mass, and you put all the 2 protons and 2 neutrons on it before the fusion reaction, and it had a mass of whatever it was, like 4, if you was to take all the particles after the fusion reaction and put them back on that scale, you'd find that it's got a mass of like 3.999999999 something. A tiny, tiny, tiny bit of mass seems to have just disappeared. How is that possible? How is it possible that mass just seems to disappear? Where could that mass have gone? So just, if you want to pause the video here, do so. Just have a think about where could that mass have actually gone? Because you've just looked at it, you might be thinking, oh, it's that neutron that's flown off. No, I'm including that in my calculation. Like if I was to take those 3 particles there and that neutron that flew off and I put them together again and then weighed them, it'd still be 3.9999, whatever it is going to be. I'm telling you that in total, some of the mass appears to have disappeared. There's a little bit of a tip there for you. That picture might help you out, maybe, I don't know. Right, let's think about where that mass could have gone then. The missing mass gets converted into energy. Okay, now if you have a look at my boy Einstein's hat there, E equals mc squared. What could E equals? What is E? Well, we've used the letter E in equations before, haven't we? And like the specific heat capacity equation, E refers to energy. So his equation says the amount of energy is equal to mc squared. Well, what could M be? What we just talked about? Yeah, the mass. So the energy is equal to the mass multiplied by whatever this substance C is, squared. Well, I can tell you now that C is the speed of light. So this equation says that the amount of energy that you can get out of is equal to the mass multiplied by the speed of light squared. That's a frigging big number. So even if you've got a tiny mass, you can still get a massive amount of energy out of it. Okay, so that is what E equals mc squared means. It means that if you can convert mass into energy, that's the equation you'll use. You can figure out how much actual energy you get for a specific amount of mass that you've used. Right, so in contrast to fission then, fusion is the joining of atomic nuclei, and there's a couple of pictures there that look dead confusing to start off with, but if you ignore this bit at the bottom to start off with, this is uranium-235 splitting into 2 daughter nuclei, emitting 3 neutrons and giving out some energy. So this is fission. This at the bottom is fusion. You can see you add up a couple of isotopes. In this case, it's not deuterium and deuterium, it's deuterium and tritium. But we're not really interested in that. Just worry about the mass before and after. So this is fusion at the bottom, and this gives out energy, a neutron, and makes helium. Okay, so it says task 2 on your sheet. I've done this a little bit differently. It's got some of the key points of fission and fusion, and I'm going to show you a diagram in a second, a Venn diagram, and I want you to put the correct letters in the right spot on your Venn diagram. Okay, if you're stuck, these pictures might help. And in a minute, there's an overlap that I want you to think of. Does anything fit in that overlap in the middle? Okay, so what I mean is this. These are the comments that I want you to use. I want you to read it. A heavy nucleus breaks up to form 2 lighter nuclei. So is that fission, or is that fusion, or is it both? Think about where you'd put that letter on there. I don't mind if you pause this video and write it down. Do whatever you want to get this done. I want every single one of these letters in either fission, fusion, or both. Now, once you've done, there might be some things that aren't included on this table at all that you might want to use to describe what both of these things do. What do these things have in common? You might need to put that in there. Okay, so just pause the video now. Take as long as you like on that, to be honest with you. So which of these relate to fission? Which of those letters relate to fusion? And then after you've sorted all those letters out, the bit in the middle, the both section, the overlap in your Venn diagram is going to be empty. What do these things have in common? Just describe it. There's no letter there to do it. Just describe it yourself. So pause the video, spend a few minutes doing that, and then I'll show you the answers in a second. Right, so let's have a look at the answers to this then. It should look like this. So in fission, you should have A, D, E, G, H, K. Now, if you're not sure what those letters refer to, just go back. I'm not going to, because if I keep popping back like this, it's going to get dead confusing, okay? So those are for the things for fission. Those are the things for fusion. And then the overlap, I'll be honest with you, when I've done this in a lesson, people get a bit stuck on the overlap. They can't figure out what it's got in common. But I'm going to show you these two things that they've got in common, and you're going to go, of course that makes sense. So people try to usually overthink this bit a little bit, okay? What do fission and fusion have in common then? Well, both release energy. They've both got that in common. If I had a fission reaction going off, it'd be giving out energy. If I had a fusion reaction going off, that'd be giving out energy as well. The other thing that they both have in common is that they both emit neutrons. So if I go back a little bit, whoop, you can see in fission, neutrons getting released. You can see in fusion, neutron getting released. You can see in fission, energy gets released. In fusion, energy gets released. Okay, so I've gone back now, so you can actually look at those letters if you want to. So yeah, that is how I wanted you to sort out. So we've got the differences between fission and fusion, and you've also thought about a couple of the similarities, and there again is the answer if you need it. Okay, so that's the difference between fission and fusion. Okay, so if fusion is so great, why aren't we using it instead of fission? Because then there are benefits to fusion that far outweigh fission. There's more energy released from fusion than there is in fission. There's no radioactive waste produced. The materials that we use for it are really abundant on Earth, easy to get and not dangerous. Why aren't we using it instead of fission then? Because it's basically full of benefits and got very, very few drawbacks. Well, I'll tell you the reason, okay? If you have a look at this, if I was to take, and you can see these are 2 isotopes of hydrogen here, if I was to try and push them together, look at the charges on them. Look at the charges in those nuclei. One's got a positive charge, the other's got a positive charge. Now I'm sure at some point in your life you've taken a couple of magnets, pole to pole, like north to north, and you've tried to push them together and you felt that force of repulsion. The force of repulsion between 2 magnets is basically nothing compared to the force of repulsion between 2 positive or 2 negative charges. You try and force them together and you aren't going to be able to do it, essentially, not on Earth as it currently stands, not easily anyway, okay? So high temperature and density is needed to overcome the repulsion between protons so the nuclei can fuse. This is happening in the sun, but it's happening in the sun because of insane temperatures and massive pressures. That makes it possible to actually physically force these things together. On Earth, it ain't that easy, okay? So fusion occurs in the sun due to enormous pressure and temperature. For fusion to occur on Earth, we'd need a temperature of around 100 million degrees C. That's quite warm, okay? So that is why it's not happening on Earth currently. We have had instances where we've managed to get fusion to happen, but it doesn't last very long. And the other problem with it is that at the minute, the amount of energy that we put into getting the fusion reaction to happen is actually more than the amount of energy we get out. So it's not currently worth doing it. But when we figure out how to do that, how to get cold fusion is what it's sometimes referred to. The idea of somehow getting these nuclei to fuse together without having to get them really hot or subject them to insane pressures. When we figure that out, our energy worries as a race and as a planet are basically over, because fusion is going to take over everything. This is a nice little animation that shows you what I'm basically going on about here. So without heat and pressure, you can see those positive charges, which are representing the nuclei in this case, come near each other and go, "Whoop, no, don't want anything to do with you." They're both the same, so there is an enormous force of repulsion. However, if we get them really, really hot and we subject them to massive amounts of pressure, there's enough energy there to physically force them together, whether they want to repel each other or not. And it's that fusing together of those nuclei that converts a tiny bit of mass into a massive amount of energy. Okay, so that is what's happening with fusion. There's a couple of the reasons why we can't do it on Earth at the minute, but we're hoping that one day we can do it. Right, there's some exam questions there that I want you to have a go at. Okay, try them. I'll be honest with you, this causes some confusion normally, but it's important that you know. In fact, I'll read through the first bit with you. At the very high temperatures in the sun, hydrogen is converted into helium. It takes 4 hydrogen nuclei to produce 1 helium nucleus. So if you take 4 hydrogen, that doesn't make any sense, does it? 4 hydrogen nuclei would... Forget it, we'll just carry on with it. It takes 4 hydrogen nuclei to produce 1 helium nucleus. The table shows the relative masses of hydrogen and helium nuclei. Okay, so you can see hydrogen's got this mass, 1.007825, and helium's got a mass of 4.0037. Okay, use these figures to calculate what happens to the mass of the sun as hydrogen is converted to helium. Well, think about it. If you convert 4 of these into one of those, is there a difference in those two numbers? What's that multiplied by 4? And then whatever that number is going to be, compare it to this. So what happens to the mass of the sun? It is changing. I'll give you a little clue there. Okay. Use your answer to part A to explain how the sun has been able to radiate huge amounts of energy for billions of years. Think back to what fusion involves and relate that to the idea that fusion is happening in the sun. You should be able to come up with an answer there. Nuclear fusion in the sun releases large amounts of energy. Explain what is meant by nuclear fusion. Rewind the video if you need to. Why is energy released by such nuclear fusion reactions? Again, the answer's been in the video so far. So pause the video there. How many marks? Is it 10? Spend 10 minutes. Spend as long as you like, really. Just pause the video. Give those a go, and then I'll get back to you with the answers in a second. Okay, let's go through the answers to that then. So these are the answers on the right hand side. Right, so you should have calculated that 4 multiplied by this, which is the mass of 1 hydrogen nuclei, is equal to 4.0313. Now that's interesting because 4.0313, the mass of helium is not that, okay? So there's a loss of mass, or you could say 0.0276 has been lost, or it's missing 0.69%, so the mass has gone down. Now you should have known that already, really. Without calculating it, you should have known in your head, well, when you fuse that together, a bit of mass is lost, okay? So that's what's happening. So what happens to the mass of the sun as hydrogen is converted into helium? It decreases, okay? You should have had that. So that's where you get the marks from. If you've got 4.0313, that's 1 mark. If you said there's a loss of mass, that's 1 mark. And then if you say how much has been lost, you can get the 3rd mark then. Use your answer to part A to explain how the sun has been able to radiate huge amounts of energy for billions of years. You need to get the idea that the loss of mass results in the release of energy. We talked about that earlier on when we were talking about what fusion is. But small loss of mass results in huge energy release. So you can say that it's been losing mass in these fusion reactions, and that mass has been converted into energy. Now it only takes a tiny bit of mass to create a ridiculous amount of energy. So, and obviously this isn't just happening one at a time. All these fusion reactions are happening at the same time in the sun, so it's producing just an enormous amount of energy. Question number 2. Nuclear fusion in the sun releases large amounts of energy. Explain what is meant by nuclear fusion. So you should have had here the nuclei, if you've mentioned nuclei, that's 1 mark, of hydrogen or smaller atoms, that's worth the 2nd mark. Join to make helium or larger atoms, so that's worth the 3rd mark. So if you said nuclei that are small or of hydrogen, join together to form something larger, there's your 3 marks. Question 2b, why is energy released by such nuclear fusion reactions? That's because the mass of the large nucleus, or the large atom, I could have said atom there, is less than the mass of the smaller ones combined. And because of that, because there's less mass after the reaction than there was before, it's some of that mass that gets converted into energy, okay? So mass loss converted into energy, or small mass loss given a large amount of energy, okay? So that is the answers to those. Now what I want to show you here is a examiner's report, because these were actual exam questions from an actual exam paper. And after the exam papers are sat, the examiners sit down and say, right, how did everyone do on this question and this question and this question? They kind of analyse it. And then they talk about what was common in terms of mistakes, whether students did particularly well on a question or particularly bad on a question. So let's have a quick look what the examiner's comments were for this. Right, so for question 1A, it says, use these figures to calculate what happens to the mass of the sun as hydrogen is converted to helium. It says many candidates correctly use the figures to demonstrate a very slight loss of mass during the fusion reaction, so most students are able to do that. Okay, so that in itself isn't much use to you, that comment, but others might be. Question B says, use your answer to part A to explain how the sun has been able to radiate huge amounts of energy for billions of years. It says here that relatively few candidates related the loss of mass from part A and the huge energy output referred to in the stem of part B by pointing out that mass is equivalent to energy. So there's this thing called mass energy equivalence. You can convert mass into energy with a huge release of energy, and then it says as compared to chemical reactions involving the same number of atoms. Though this was recalled knowledge, the recall was strongly cued. Okay, so it was the idea that they wanted you to remember something, but they give you a big hint there, talking about it's radiating huge amounts of energy. And in a previous question, it had you working out that there was a loss of mass. So if you'd have put those two things together, you should have clicked, oh yeah, I remember in that lesson when we were talking about a bit of mass can be converted into a massive amount of energy. So that's the examiner comments for the first two questions. Question 2 says, nuclear fusion in the sun releases large amounts of energy. Explain what is meant by nuclear fusion. And from the examiner's comments, it says there were many correct answers, the common error being to fuse atoms rather than nuclei. Okay, so a number of candidates described fission rather than fusion, so that's a couple of common mistakes there. So remember, we're talking about nuclei being fused together, and we're talking about fusion. Remember, fusion as in fusing something together. So don't get that mixed up with fission. It's definitely fusion, and it's definitely nuclei that are being fused together. Okay, don't refer to them as atoms, because it's not the outer electrons that we're interested in, as I mentioned way back at the start of this topic. It's the nuclei. Okay. Question 2b, why is energy released by such nuclear reactions? And it says in part B, some candidates gained both marks, but many just gained 1 mark for the mass reduction as fusion occurs. So apparently a lot of people said the mass goes down, but then stopped there. They failed to complete the answers by saying the mass loss was then converted into energy. So you need to say, for the marks, you need to mention, yeah, the mass goes down, but then you need to basically comment on, well, what happens to that mass? It's decreased, and you have to mention that it's decreased because it's been converted into energy. Okay. A minority wrote about fusion as an exothermic chemical reaction. So it didn't really ask you about that in that question, so why people would write about that, I'm not really sure. All you needed to say there was the mass goes down because energy is given out. It converts mass into energy. Again, that term we used a second ago was mass energy equivalence, and we're talking about some ridiculous numbers like this. What was the loss in mass here? 0.0276. I'm just going to very quickly calculate something for you. I'm going to find my calculator. Right, I told you that E equals mc squared. The energy is equal to the mass. We worked out the mass earlier on, 0.0276. 0.0276. So that's the mass multiplied by the speed of light squared. So we're going to multiply that by 300 million. And then we're going to square that. I think I need to convert my theorem like that. So that equals 2.48 and then 5 zeros to the power of 15 joules of energy. That is a ridiculous amount of energy. And bear in mind, that's one episode, or that's one fusion reaction, I should say. So massive amounts of energy being released from just one fusion reaction. And this is happening, I don't even know how many times in the sun. I wouldn't like to give you a number. Okay then, so you can't use your planner page to indicate true or false to the following questions, because, well, I can't see your planner page, so it's a bit pointless, isn't it? Fission is the joining together of atomic nuclei. So if you think that's true, you'd be giving me a green page now. If you think it's false, you'd be giving me red. You should have gone for red there. It's not fission, the joining together of atomic nuclei, it's fusion. Fusion. Don't get those mixed up. Remember, fusion, fusing. Next one, the products of fusion have a slightly higher mass than the reactants. So is that true, or is that false? You should have said that is false. The products of fusion have a slightly lower mass. Remember that the mass goes down as it's converted. That small amount of mass gets converted into energy. Okay, mass energy equivalence. So that one is false as well. The mass lost in a fusion reaction is converted into energy. So is that true, or is that false? You should have said true there. Okay, I've put lost there. It's not lost. The mass decreased because it was converted into energy. It didn't disappear. But that one is true. Yeah. So as the mass goes down, the amount of energy given out increases. The force of attraction between atomic nuclei is why fusion on Earth is difficult to achieve. So is that true, or is that false? You should have said false there. It's not the force of attraction, it's the force of repulsion. We can't overcome easily those forces of repulsion between two similarly charged substances. So if I've got two nuclei that are both positive and I try and force them together, I'm not going to be able to do it. I need an insane temperature and I need an insane amount of pressure to get that to happen. For fusion to occur on Earth, a temperature of around 100 million degrees Celsius would be required. True or false? You should have said true there. Again, massive amount of energy required in order to actually get fusion to occur. Bear in mind that on the sun, it's already hot from all the other fusion reactions. They're all giving out energy, so therefore that isn't that hard to entertain. Okay, I think. Yeah, you could go back to your outcomes and have a quick look at those. Can you do those now? Okay, so can you describe the similarities and differences between fission and fusion? Can you explain the difficulties with using fusion as an energy source on Earth? And can you explain how energy is produced via fusion by comparison of reactants and products? If you can't do any of those, rewind the video, go over it again. If my explanation didn't cut it for you, go onto YouTube, find somebody else explaining it. Go onto Bitesize, see if that helps you out. If you've got a revision guide, use that. So you need to make sure that you're okay with all these outcomes, because if you're not, you're only kidding yourself, really. So practice those. Make sure you're in a position where if an exam question asks you about this, you know exactly what to say. Hopefully that's been helpful for you. I'm going to call it a day there.